Write the IUPAC names of these compounds. We should give preference to OH group, carbon bearing OH group. So that is why this is first carbon, second carbon, and this is third carbon. So it is 2-methyl propane 1 mole. Now same, we have to give preference to the carbon bearing OH group. So from left to right the same, but here 3 carbon atoms are there in the side chain. Then we have to take this as the main chain, longest continuous chain. So it is 3-ethyl, 3-ethyl hexane 3 mole. Double bond and OH groups are there, but we have to give preference to OH group only. So 1, 2, 3, 4. Therefore, it is but 2, 3 in 2 mole. Now again 1, 2, 3, 4. 1, 2, 3, 4. So you can proceed from this. Therefore, it is a 3-methyl butane 2 mole. So we have to give preference to OH group carbon, second position, third position. So 3 carbons, prop 2 ine 1 mole. Phenyl group is substituent here. This is substituent phenyl group. Now 1, 2, 3, 4, 5. So therefore it is 3-phenyl prop, no, pent, sorry. In 3 mole. Okay. So these are called cyclic alcohols. Cyclic alcohols. This is cyclopropanol, cyclobutanol, cyclopentanol. Now this is cyclopentanol, in which at second carbon methyl group is there, therefore it is called 2-methyl cyclopentanol. Nomenclature of dihydric alcohols: CH2, CH2, OH, OH. Now it is two carbons are there. It next single bond N, and positions of OH groups are 1 and 2, and to indicate two OH groups in the organic compound, use diol, numerical prefix diol. So you have to mention the position of OH groups also, 1, 2 diol. Right? So here you should not drop E. E must be there because here suffix is started with secondary suffix started with D. It is not a vowel. So therefore you should not drop E. Ethane 1, 2 diol. Now C. CH3, CH2, CH2OH, and here CHOH. So now it is propane 1, 2, 3, right? So propane 1, 2 diol. CH2OH, CH2, CH2OH. Now this is first carbon, second carbon, third carbon. So this is propane 1, 2, 1, 3 diol, 1, 3 diol. CH2OH, CHOH, CH2OH. Now see, this is 1, 2, 3 propane single bond, 1, 2, 3 triol. What is the important common name of this compound? Glycerol or glycerin. Right? Now, see, one time, long back only, in the state level medical entrance examination, they asked a question. How many primary alcohol functional groups are present in glycerol? See, CH2OH, this is primary alcohol functional group. CHOH is secondary alcohol functional group. COH is tertiary alcohol functional group. CH2OH, CHOH, CH2OH. So this is primary alcohol functional group. This is primary alcohol functional group, and this is secondary alcohol functional group. So two primary alcohol functional groups and one secondary alcohol functional group is present in glycerol. Now, so now this is treated as first carbon, second carbon. So therefore 2-methyl phenol. This is actually orthocresol. OH CH3. This is metacresol. So this is one second carbon, third carbon. Therefore, it is 3-methyl cresol. This is actually paracresol. So this is 4-methyl 4-methyl phenol. See here, it is phenol. Okay, right. Similarly, OH group, bromine is present, then it is 2-bromophenol. 2-bromophenol. Now, for example, this is OH group. Here, bromine is there, NO2 group is there, for example. Then it is 2-bromo 4-nitrophenol. All become substituents only. Now, this is OH, NO2, NO2, NO2. So this is first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. So therefore it is 2, 4, 6 trinitrophenol. Trinitrophenol. Important commercial name or common name, picric acid. Is a very strong acid. Now this is first carbon, second carbon, 2-amino phenol. Now see this one. This is OH. Here COOH is there. Now COOH functional group, carboxylic acid functional group. So according to IUPAC, we should give preference to carboxylic acid functional group. So therefore, it is a benzoic acid but not a phenol. This compound is not treated as phenol. Actually, this is phenol, but it is not treated as phenol in IUPAC system because between OH group and COOH group, we have to give preference to carboxylic acid functional group. Therefore, this is first position, second position, third position, fourth position, fifth position, sixth position. Now it is 2-hydroxy because OH group becomes now substituent 2-hydroxy benzoic acid. Very, very important common name, salicylic acid. Salicylic acid. Now, two functional groups are there, OH group, CHO group. CHO group aldehyde, we should give preference to aldehyde functional group according to IUPAC system. So, it is a benzaldehyde, first carbon, second carbon OH group substituent, 3, 4, 5, 6. Therefore, it is 2-hydroxy benzaldehyde. Right? Important common name is there, salicylaldehyde. Salicylaldehyde. So, in the IUPAC nomenclature, next. Isomerism in alcohols. Isomerism in alcohols. See, they exhibit chain isomerism. To exhibit chain isomerism, organic compound should contain at least how many carbons? 4 carbons, right? So 1, 2, 3, 4 OH. So it is nothing but N-butyl alcohol, butane, 1 O. No need of E here. Next, see, CH3, CH, CH3, CH2OH. This is 2-methyl propane, 1 O, 1, 2, 3. So, these two compounds have same molecular formula, C4H10O, and they differ in number of carbon atoms in the longest continuous chain. So here 4 carbon atoms are there in the chain, here 3 carbon atoms are there in the chain, therefore these two are examples of chain isomers. Positional isomerism. This isomerism arises due to the position of OH group in the alcohols. Now I am giving a very good example. N-propyl alcohol and isopropyl alcohol. CH3, CH2, CH2, OH. CH3, CHOH, CH3. So this is propane 1 mole. This is propane 2 mole. These two compounds have same molecular formula and differ in the position of the OH groups. Therefore, they are examples of positional isomers. They are examples of positional isomerism. Functional isomerism. Functional isomerism. See, alcohols and ethers having same molecular formula are examples of functional isomers. See, for example, CH3CH2OH, molecular formula C2S6O, CH3OCH3, molecular formula same C2S6O. OH functional group is present, here O is there. It is alcohol and it is ether. So, same molecular formula but differ in the functional group. Therefore, these are functional isomers. Now, another important stereoisomerism is optical isomers. See, any alcohol having at least one chiral carbon exhibit optical isomerism. See, for example, secondary butyl alcohol is the first alcohol exhibits optical isomerism. Secondary butyl alcohol. This is the smallest alcohol which can exhibit optical isomerism because methanol do not exhibit, ethanol do not exhibit, N-propyl alcohol do not exhibit, isopropyl alcohol do not exhibit. So N equal to 4, secondary butyl alcohol only exhibit optical isomerism. See, CH3, CH2, C, CH3, hydrogen, OH. So, one side methyl group, other side ethyl group, and hydrogen here OH group. So, this is the carbon bonded to 4 different groups. Therefore, it is chiral carbon and therefore compound exhibit optical isomerism. See, suppose CH3, CH2, CH2OH. This also exhibit optical isomerism, but see here at this carbon, one is hydrogen, the other should be deuterium like this. This is hydrogen, this is deuterium. Now it became chiral carbon and exhibit optical isomerism. But here I am asking the smallest alcohol, means you have to take only pure hydrogens and no substituents, no deuterium, no tritium. The smallest alcohol which can exhibit enantiomerism is butane 2O. Right? Methods of preparation of alcohols. Number 1, from alkyl halides. Now, when alkyl halides are treated with aqueous KOH, then X minus is replaced by OH minus. So, OH minus ion attacks from the back side exactly 180 degrees with respect to the leaving group, then we will get ROH, alcohol X minus. So it is SN1 mechanism, SN2 mechanism. SN2 mechanism. Okay. Now see, for example, CH3CH2Br aqueous KOH gives rise to CH3CH2OH. CH3CHBr CH3 aqueous KOH, then CH3CHOH CH3. This is primary alkyl halide, this is secondary alkyl halide. Reaction proceed via SN2 mechanism. Reaction proceed via SN2 mechanism. If it is a tertiary alkyl halide, should not use a strong base like sodium hydroxide or potassium hydroxide. The water is a weak base, it is enough, then you will get tertiary butyl alcohol. This reaction takes place via SN1 mechanism. Suppose in case of tertiary alkyl halides, if you use aqueous KOH, tertiary butyl alcohol is formed, but it is minor only, but major product is isobutylene. Isobutylene. So that means dehydrohalogenation takes place. Dehydrohalogenation takes place. So that is why we should not use aqueous KOH or sodium hydroxide to get tertiary butyl alcohol, a tertiary alcohol. For tertiary, to get tertiary alcohol, reagent is water. Hydrolysis only. Simple hydrolysis of that compound will produce alcohol, tertiary alcohol. But for primary and secondary alkyl halides, aqueous sodium hydroxide or aqueous potassium hydroxide is required, because in SN2 reaction, rate of reaction directly proportional to the concentration of alkyl halide and also concentration of the base also. So rate of reaction depends on both alkyl halide and also base. So therefore, a strong base is required for SN2 reaction. In case of SN1, the rate of reaction directly proportional to the concentration of alkyl halide only. So therefore, a weak base is sufficient to carry out SN1 mechanism. So what is the product formed in the reaction? This is the reaction because configuration is inverted. So this is called Walden inversion because reaction takes place via SN2 mechanism. This is chiral carbon. Second method, reduction of aldehydes or ketones. Reducing agents used are hydrogen in the presence of nickel, platinum or palladium, sodium in ethyl alcohol, ETOH means ethyl alcohol, lithium aluminum hydride, sodium borohydride, LiAlH4, lithium aluminum hydride, NaBH4, sodium borohydride. So, aldehydes, both aldehydes and ketones, RCOR, reduces as alcohols, RCH2OH, RCHOH, R. See, remember very simply like this, RC double bond O H. Add two hydrogen atoms. Pi bond undergo fission. No pi bond. Everything is same. Pi bond is not there. Now add one hydrogen here, add one hydrogen here. So this is nothing but RCH2OH. So you will get a primary alcohol. Now for example, RC double bond O R dash. Okay. Now see, very simple. Whatever it may be the reducing agent, whether it is sodium ethyl alcohol, lithium aluminum hydride, or sodium borohydride, hydrogen, simply hydrogen, nickel, platinum, palladium, whatever it may be. See, R, C, pi bond undergo fission. So, everything is same. Add two hydrogen atoms. One is to oxygen, one is to hydrogen. So, this is a secondary alcohol. So, remember, these are the reducing agents. These are the reducing agents. Remember, aldehydes give or reduces as primary alcohols. Ketones reduce as secondary alcohol. That's all. Reducing agents are hydrogen, nickel, platinum, palladium, sodium in ethyl alcohol, sodium dissolved in ethyl alcohol, lithium aluminum hydride or sodium borohydride. Aldehydes reduce as primary alcohols, ketones reduce as secondary alcohol. Remember, it is not possible to prepare a tertiary alcohol by this method. it is not possible for us to prepare a tertiary alcohol by this method, because aldehydes reduce as primary alcohols, ketones always reduce as secondary alcohols. Acetone. So this is CH2OH is there, primary alcohol. CHOH is there, secondary alcohol. By reduction of carboxylic acids, reducing agent used is lithium aluminum hydride. Most important. First step is lithium aluminum hydride. Second step is hydrolysis. Lithium aluminum hydride, after that immediately treated with water. So not only reduction, remember, not only reduction, after treatment of carboxylic acid with lithium aluminum hydride, immediately hydrolysis is carried out. So now you can say alcohols can be obtained. Alcohols can be obtained by the reduction of carboxylic acid in the presence of lithium aluminum hydride followed by hydrolysis. Clear? Remember, not only reduction and plus hydrolysis. So RCOOH, general reaction, RCOOH, first step, lithium aluminum hydride. Sometimes lithium aluminum hydride is represented as LaH also. Sodium borohydride, for example, it is SBH. Or CH2OH. So we'll get generally primary alcohol. Now, CH3COOH. First reduction with lithium aluminum hydride. Second step, hydrolysis. You will get CH3CH2OH. Here number of carbon atoms are 2. Here also number of carbon atoms 2. Clear? Next. By reduction of esters, same first step, reduction with lithium aluminum hydride. and second step hydrolysis. RCOO R dash. This is ester. Lithium aluminum hydride and second step water. Then you will get RCH2OH plus R dash OH. So you will get a mixture of alcohols. You will get mixture of alcohols. Clear? For example, CH3, CH2, C double bond O, O, CH3. This is methyl propanoate. This is the IUPAC name of the ester. This is methyl group. This is propanoate. CH3, CH2, COOH. Propanoic acid, CS3, CH2, COO, propanoate. To this propanoate, methyl group is bonded. Therefore, it is methyl propanoate. Okay. Now, remember, simply it is not a mechanism. Remember, you split this ester into two parts. Then, how many carbon atoms are there here? 3. So, write alcohol with 3 carbons. Next, remaining part, add hydrogen. So, you will get propane 1 mole and methanol. These are the products obtained in the reduction of methyl propanoate in the presence of lithium aluminum hydride followed by hydrolysis. Very important reaction. From Grignard reagent, HC double bond OH. See, RC double bond OR. This is carbon chain totally. Now, carbon and oxygen. Carbon is less electronegative and oxygen is more electronegative. Pi electrons are displaced towards oxygen. So, carbon gets partial positive charge, oxygen gets partial negative charge. For example, Grignard reagent. Generally, we represent Grignard reagent by RMGX. CH3, R is CH3, Mg, Br. For example, magnesium is metal, carbon is non-metal. Thus, this is the bond between metal and non-metal, is it not? So, it carry positive charge and carbon acquires partial negative charge. So, remember, in Grignard reagent, this part of the reagent carry partial positive charge, alkyl part of the reagent gets a partial negative charge. So, automatically in C double bond O, carbon carry positive charge, partial positive charge, and oxygen carry partial negative charge. Therefore, the alkyl part of the Grignard reagent will attack the C double bond O of carbon, and Mgx will attack partial negative charged oxygen. Is it clear? Now we took formaldehyde. Now R minus Mgx plus. R minus will attack C double bond O. Pi electrons are completely displaced towards oxygen. Then you will get HCH O Mgx and R. So this is an addition compound. Addition compound. Now, followed by hydrolysis. So remember, this part undergo hydrolysis. HOH. So HCH, HCH, ROH. So what is the byproduct formed in the reaction? MgXOH. Now see, RCH2OH. So it is a primary alcohol. So remember, very, very important. Formaldehyde plus Grignard reagent. Next, followed by hydrolysis gives primary alcohol. Very, very, very important. Now, for example, except formaldehyde, any other aldehyde, here R is not equal to H. R is not equal to H. Now, R dash Mgx. See, R dash will attack the carbon and Mgx will attack the oxygen. So, what is the compound you will get? R, C, R dash, O, Mgx, H. Hydrolysis. So, this bond undergo cleavage, H, OH. So, you will get RCH, R dash, OH plus byproduct is MgX, OH. So, this is a secondary alcohol functional group. Now, RCHO, R is not equal to H plus Grignard reagent followed by hydrolysis yields a secondary alcohol. Very, very, very important, remember. Very, very important for entrance examination. Now, for example, RC double bond O R, R dash, any ketone here, any ketone, remember, R dash MgX. So, R C R R dash OMGX and followed by hydrolysis. Add hydrogen here, OH here, RCR dash OH plus MgXOH. So this is a tertiary alcohol. So any ketone addition of Grignard reagent and followed by hydrolysis yields a tertiary alcohol. So this reaction is very important, and again I will discuss the same reaction once again with examples in the next class. Very important.